function, trigonometric function and unit circle. So here we are trying to find the relationship between the sixth trigonometric function and the unit circle. We see here a cosecant is in the same direction with the sine vertically, and the cosecant intersects with the cotangent. So here is some relationship between sine, cosecant, and cotangent. If we look, for example, the secant, cosine are in the same direction, so here we see same relationship in the unit circle, and a tangent is intersected with a secant. But let's try and see if we can find some relationship analytically. And if we look here in this triangle, this is a right triangle. Here is a x, y, and equal to 1 according to the Pythagorean theorem. X squared plus y squared is equal to 1 because x squared and y squared, x and y are sides of the triangle, and 1 is the hypotenuse, is equal to 1. On the other hand, if you look here, the cosine, the x is equal to the cosine, so this we can write a cosine square x plus sine square x, because x is equal to the cosine, plus sine square x. We can create this identity, trigonometric identity. Sine square x is equal with 1. But because we are looking here to find the relationship with the, let's try with the sine and secant. So if we are trying with the sines to find this relationship, we divide everything by sine square x. And if we divide everything, whole the equation, by sine square x, we will get as follows. Cosine square x divided by sine square x is a cotangent square x. So it's a cotangent square x. And here is a plus. We write in the way how it is. And now sine square x divided by sine square x is equal with 1. And this is equal. On the right side, 1 divided by sine square x, we can write in this way, 1 divided by sine square x by sine square x. And now, just let's do the last step. We see the relationship between a sine square x and a sine and a cotangent. But now, cotangent, let's write to the left side in the way how it is. Cotangent square x plus 1 is equal. Now we're looking with the cosecant. Can we find the relationship? But we already know 1 over sine square x is equal, 1 over sine x is equal with the cosecant x. But because it's a square, we can write here cosecant square x. So we already see this relationship between a cotangent, cosecant, and sine. But now let's look at the other side. Let's see the secant, tangent, and the cosine. Do we have any relationship? We go to this equation here. What we have to this identity, trigonometric identity. We have a cosine square x plus sine square x is equal with 1. We go to the same identity. Plus sine square x. Let me write it as smaller because I want to fit every whole equation here. Is equal with 1. And now we are looking for cosine to find this relationship, and we divide the whole equation by the cosine square x. Cosine square x. If we divide here, cosine square x divided by cosine square x is 1, plus sine square x divided by cosine square x is a tangent square x. So we have this equation here. We already looking now those relationship between tangent and cosine. And here is 1 divided by cosine square x. So we already see here the relationship between cosine and tangent square x. now we're looking with a secant. And we already know the left side we can write in the way how it is, so we don't have to change anything. Tangent square x is equal. But according to the trigonometric identity, 1 over cosine square x is equal to the secant square x. Secant square x. And now we found this relationship between tangent, secant, and cosine. But now let's go down and let's see the graphs of the function secant and cosecant of this relationship. So with the red function here, the red function here is a cosine x, and a secant is whenever is here, for example, the maximum point in the amplitude what reaching the cosine, here is the minimum of the secant in this side. Whenever is a minimum here of the sine, is a maximum here down of the cosine in the negative part, if we are looking for negative part of the secant. And the period, the asymptotes is in a pi over 2, minus 3 pi over 2, etc. in those points. Every pi, but pi over 2. So if we are looking here for the domain, x is from minus infinity to infinity, except x is different from 2k plus 1 times pi over 2. But the k is the integer, as I said before, is any integer. K is element of integer. So, and the range of the function is from minus infinity to minus 1 here, and is from 1 to infinity, the range of the secant. And if we are going to cosecant has a close relationship with the sine x. Whenever the red function here with the intercepted with the dash is y is equal sine x, and those are cosecant. When in the maximum of the amplitude, whenever it reaches the maximum in the amplitude here, 1, the function sine x, is a minimum for the cosecant. And whenever is a minimum for the sine x, is the maximum in the lower side, negative side, is the maximum for the cosecant function. So if we look at now the domain of the cosecant function, y is equal to cosecant x, the domain is all the real numbers, except x is different from k times pi. K is integer, is element of integer. Can be 0, plus minus 1, plus minus 2, plus minus 3, etc. to infinity. And if we are looking, whenever is a minus pi, 0, pi, 2 pi, those are asymptotes. Here is not continuous in those points of the cosecant. And now, but the sine, you see, sine x is a continuous everywhere. If you look, for example, the domain of the sine x is from minus infinity to infinity, and the range is from minus 1 to 1. If you look for the range, and in the same way, has an even cosine, and the cosine has the same domain from minus infinity to infinity, and the range is from minus 1 to 1, have the same range. And for the cosecant, as I said before, we have the domain is from minus infinity to infinity, except x is different from k times pi. K is element of integers, and the range is from minus infinity to minus 1, from minus infinity to minus 1, and is from 1 to infinity, but includes 1, and here includes minus 1. So this is the range.